Okay, so thanks very much, Faris, and thank you to the organizers. I know you've had a particularly difficult time organizing this particular workshop, so I just want to express my thanks for all your efforts there. So the title of my talk is a bit of a tongue twister, Teaching Human Teachers to Learn to Teach Robot Learners. And I want to, firstly, before I start, flag the contributions of my two former PhD students, Marina Aoyama and Aaron Senna, who are sort of instrumental to this work. So let's see if this clicks. Here we go. So to motivate what I want to talk about today, so we're very much interested in collaborative robots, which I'm sure everyone's familiar with, and in particular, how to do programming by demonstration. And over the last few years, we've been working actually quite a lot with the agriculture and horticulture industry in the UK, who are actually currently facing a bit of a labour crisis. We have some sort of local political conditions and more global conditions that mean it's actually quite hard to get migrant seasonal labor to come in and work in these kinds of jobs. So what they're looking for is an easy solution to do sort of tasks in the production of basically plants and crops. So here actually is a kind of a little mock-up or sort of a trial of using a collaborative robot to do a real horticultural production task, which is, so they sell these trays of plants to consumers, and they should all be of a uniform sort of quality and specification. So one particular task is what we call the collation task, which is to basically dispose of unhealthy plants or plants that don't grow to the right size. And that's just one example among many kind of manual manipulation tasks that an average horticultural worker needs to do. So our idea is, can we use a learning from demonstration approach to do this? And again, I'm sure most people are familiar with the kind of overall concept of learning from demonstrations, where we assume that we've got demonstrations from people from which we can record data and use that data to form models, for example, performance metrics or control policies or whatever. From those derive a controller and pass it to the robot. And hopefully the robot is able to reproduce the desired behavior. And if it's not very good at that, then it can actually go back to the human and ask for further help, ask for more demonstrations or other kinds of feedback. So as we just saw in the last talk, there's been quite a lot of work in terms of the algorithmics of doing the learning and doing the control. The thing that I want to talk about particularly today is the human factor in this loop. So how can we get people to be good at interacting with robots in this kind of way? Or more specifically, how can we make it easy to give good demonstrations in this kind of framework? This is important in our sort of target domain, because you can't really expect a nursery worker to know anything about machine learning or how robots work. So for example, in that plant collation task, you want the robot to be able to pick any plant from any location and dispose of it. But a general nursery worker won't know how to teach it to do that, or how to essentially make it generalize across different locations or different types of plants. So that's the kind of challenge that we set ourselves, or that we're interested in addressing here. So the model that we've been working under, we proposed a couple of years ago, and we think it's kind of an interesting model for understanding that interaction between teacher and learner. So you've got your learner, and the learner is receiving demonstrations. I've notated them with this little B here. And from those demonstrations, they're learning some kind of controller or control policy. And using that control policy, they can then execute their reproduction of the behavior. Device. And then, so that's the learner side, right? So on the teacher side, well, the teacher, of course, is selecting the demonstrations to give, and they could also watch the reproductions of the behavior that the learner might choose to give. So our kind of sort of model of this is that from those reproductions, the teacher is forming some kind of belief of what is the state of learning of the robot. So what is the model that the robot has learned? And that will depend on what it sees from the robot, and it may also depend on sort of internal factors and biases and so on. So we're sort of notating them with Q. Based on that idea of what the robot's learned, they're then selecting what the next demonstration should be. And it also depends on what their model of the task is and any demonstrations they've given so far. So the thing that we sort of looking at the moment is, well, we think that the bit that we can influence is basically down at the bottom right here. So once we've learned our policy, we have a bit of flexibility in how we feed back to the teacher, or basically what kind of reproductions we choose to give. We can choose the start states, we can choose the lengths of trajectories, we can do various different things. So what, can we do something there as robot designers to make that teaching task a bit easier? So I'm going to describe an experiment where we tested this idea. So again, I'm going to sort of use that plant collation problem as the kind of test task. We did it also for a few other tasks, but this is kind of a nice familiar one. So we got a bunch of people to learn to teach a robot how to pick out these succulent plants and dispose of them in a bowl. Okay, so there's some details about the participants we used at the bottom here, but I think the key thing to note is that the participants we used were actual real production line workers at a nursery plant who had never ever used a robot before and had no familiarity with it. So the results we were kind of confident are actually what you get from a real user. And so the experiment was designed to test these different types of feedback approaches. So as a control, we gave people no feedback during teaching. So they would basically just give the demonstrations and that's it. And then once they were done, they were allowed to watch what the robot had learned, but it didn't really matter in the experiment. And then we gave them replays, so direct replay of the last demonstration that they were given. So what did the robot learn from that demonstration effectively? We had a case with what we call batch feedback, where we selected these 5 points, which we thought were good points for showing what the robot had learned. Those were expert selected. And then we also had a case where people were able to choose which plants they got a replay from. So for example, they might teach to pick this plant and then ask the robot, well, based on what you just learned, what would you do if I asked you to pick this plant over here? And I think the results were really interesting. So here I've got a sample, which is the efficiency of teaching against those different cases. Okay, so the efficiency is measured by the number of demonstrations that the teacher had to give to allow the robot to be successful to dispose any plant. Okay, so the first thing that you'll notice is that comparing the no feedback or the replay feedback or even the self-selected feedback cases, the performance was basically the same. And actually, there's no statistically significant difference between any of these 3 cases. Okay, so that's kind of to be expected in replay feedback, because if you're just replaying the last demonstration, you're not really seeing anything about generalization. But weirdly, in the self-selected feedback, they also didn't do very well. And that really shows that actually people are pretty terrible at choosing to get good feedback about generalization if they're novice teachers. Now the batch feedback case, this was the only case where we had a statistically significant improvement in the teaching behavior of our participants. So that shows that actually you can influence their teaching behavior provided that you design the feedback strategy well. So that was kind of really promising to us. So if we are clever in how we do it, we can actually improve people's behavior when it comes to teaching robots these kinds of tasks. So going from there, the next question was, well, okay, what can we do? How can we sort of do this in a more principled way? We chose those batch feedback points based on our insight in terms of how our learning algorithm works. But can we do this in a more automated way that's not subjective to the expert and that's kind of more transferable across different types of learning tasks or learning algorithms or plant models or whatever? So the approach that we've been pursuing to try to achieve that more recently has been to adopt a machine teaching approach. So machine teaching is a kind of maybe less well-known area where you basically have an optimization where you can optimize to find the optimal data set to give if you know something about how the learning algorithm works and you know what the task parameters that you're trying to learn are. Okay, so it's a bi-level optimization. And our kind of idea here was that, well, if we train novice teachers, if we show them what is the optimal data to give to teach a particular skill, then maybe that will improve their overall teaching behavior so that they become better teachers on other skills. And that way we don't have to solve the machine teaching problem each time. So I'm just going to report another sort of little experiment that we did to show this. So this was actually an impedance type experiment where we had a little one-link robot arm that you had to teach a couple of different skills, essentially setting the impedance gains to either do a point-to-point type movement, which would be like a critically damped point-to-point movement, or an oscillation, or different types of things like that. Okay, and because this is such a simple problem, we can derive analytically a condition on what the optimal data set for teaching this task should actually be. And it turns out to be related to the determinant of the features demonstrated. And then we can use that as a scoring system and basically feedback to our teachers whether the demonstrations that they're giving are good or not. So all the technical details you can look at in the archive preprint. So I just want to quickly sort of summarize some results from this experiment. So again, we had a bunch of novice teachers, and we asked them to sequentially go through this teaching procedure where they taught the first skill, they taught the second skill, then they taught the first skill again, but they were given some feedback, which was, if they're in the target group, that was feedback derived from the machine teaching approach. And then they taught the second skill and the first and the second, okay? And what we were trying to do here is firstly, see whether that feedback would improve their teaching behavior. Secondly, see whether they could generalize. So if they were given feedback on skill 1, would they be better teachers on skill 2? And also we wanted to see if we got any retention. So that is to say, after teaching and being switched between different skills of teaching, whether they would retain their improved performance. So so these are the first set of results. So this is measuring the teaching quality of demonstrations given by our participants according to our optimality condition. And this is measuring the error in the reproduced skill. And as you can see in the target group, you've got an improvement in the teaching quality according to our metric, and also a reduction in the teaching error. And this was statistically significant. So what that shows is that comparing teaching with no guidance and teaching with guidance, adding that guidance helps to improve their teaching behavior. So we already knew that from the plant experiment, but it was good to sort of confirm that in this separate experiment. And then the second interesting result from this was that this also is retained to different skills. So this is the comparison of the teaching quality and the error in the reproductions for the target and the control groups when they were given guidance on teaching skill 1, but then they were asked to teach skill 2. So we can compare when they were given no guidance on skill 2 and after they'd been given guidance on skill 1. And we saw, again, an improvement in the teaching quality and a reduction in the teaching error. And this was also statistically significant. So that was kind of exciting for us because that shows that you can actually generalize your teaching behavior across different skills. So that was kind of really exciting. So I think I'm going to try and finish on time. So as a very brief summary, so practical programming by demonstration in real world sort of industrial tasks require advances in the algorithms, of course, but actually they also need a consideration of the usability by the end users. That's what we're trying to achieve here. So we've shown, at least in these experiments, that teacher training actually improves learning outcomes for the robot. So the robot will learn better if you have a better teacher. Makes sense, right? But we've shown it. And we've also seen that improvements to teaching one skill allow us to generalize and improve teaching to other skills. Okay, and I would generally say that design of this feedback, although we've shown it in a couple of cases, is still quite an open issue, especially for dynamic and impedance control tasks. So I'm going to finish with maybe a minute to spare and say thank you.